Okay, so I want to make a very short video about a very important topic today, the voltage divider. The voltage divider you'll see everywhere in this course. We're going to use it for filters, we're going to use it for understanding how circuits fundamentally work with Thevenin equivalent circuits in the next video, and it's just going to pop up quite a bit. In fact, it's not much of an exaggeration to say that almost everything in this course is a voltage divider of some form. So let's think about what a voltage divider is. If I have a battery, say a 9-volt battery, and I have that in a circuit, that's the only voltage I have some integrated circuit in my circuit, or some device which needs, say, I don't know, 6 volts, or else it'll blow up. How do I get that to that integrated circuit despite only having a 5-volt, or a 9-volt rather, battery? The way to accomplish this is with a voltage divider. So we have basically some V, we'll call it V in. That's what we have. And we want a very particular voltage out, V out, say between these 2 points. How do we do that? Well, one way to do that is to make a so-called voltage divider. So we're going to divide down this voltage into that. It's a very simple circuit. 2 resistors will do the trick. So we're going to have one resistor directly after the V in, and that's going to go to the top pin of V out. I'm going to put the output in parallel with V out and wire it up this way. That's it. That's my voltage divider. So I have these 2 resistors, R1 and R2, and somehow that's going to make any V out I want with some loopholes. Okay, so let's analyze the circuit. I just want to kind of hammer home the point of this. What is the point of this? The point is we want to make a new voltage source for now from an old one. So we have some black box now. We have an input voltage and we have some circuits we don't want to touch, and it's just going to have 2 leads coming out of it. And that's going to be our new voltage source. And we want to adjust these resistors such that we get that V out. Okay, so let's analyze this. We're going to have some current flowing through the circuit. There's nowhere else for the current to go. It can't go here yet because we haven't plugged anything in yet. So what is that current? We have I is equal to V over the total resistance, Ohm's law. So that's V in divided by R1 plus R2. We're actually almost there, surprisingly. So we can also use Ohm's law for the output voltage. Note that that's just the voltage drop across that resistor. So V out, well, that's going to be equal to I, that we just figured out, times R2, V equals IR. And if we just expand that, we're going to get R2 over R1 plus R2, and V out, V in rather, will be hanging out outside that term. That's it. That's my voltage divider equation. Sometimes I write it as a ratio. V out over V in is equal to R2 over R1 plus R2. Very important equation. It's a very important topology, meaning the way that I wire things up. In this course, we'll see it quite a lot, but a fairly simple thing to analyze. Okay, that's it for the theoretical textbook voltage divider. Now let's go to some practical considerations. First of all, let's use that example we just had. Let's use that example of what do we have? We had our fictitious device needed 6 volts, and we have 9 volts. So for example, want 6 volts, we have 9 volts. Let's make our voltage divider. So we have 9 here. We have a resistor here, another resistor here, and that's going to be our output. And we want R2 over R1 plus R2 to be equal to 6 over 9, 6 volts over 9 volts, or 2/3. So what should we pick? Well, an easy way to do this is just say, well, let's let R2 equal 2. 2 what? I don't know, 2 kilo ohms. Let's say R2 is equal to 2 kilo ohms. So I have 2 over x plus 2 is equal to 2 over 3. By inspection, we can see that R1 equals 1 kilo ohm. That'll do the job. So 1K and 2K will give me the desired 6 volts at the output. All right, simple enough. A few interesting things to note about this, a few practical considerations. Suppose that I don't plug it into something. What is this voltage divider doing when I don't plug it in? Well, unlike just the voltage source on itself, it's constantly running current through it to make that 6 volts across that output resistor. How much current? Well, in this case, the current it's running is 9 volts over the total resistance, which is 1 plus 2 is 3. Even I can do that. Kilo ohms, 3 milliamps. So just even without plugging anything into it, it's constantly dissipating 3 milliamps. Power is equal to I times V from Joule's law. P equals IV, so that's 27 milliwatts, right? Because it's 3 milliamps. 3 times 10 to the minus 3 times 9. 27 times 10 to the minus 3, or 27 milliwatts of power, just doing nothing. So it's wasting a bit of power. So it's an interesting fact that if I look at the math here, I could have chosen just 1 ohm and 2 ohms. I'd still get 2 over 1 plus 2. I get the same thing. All that matters actually is the ratio here. We can kind of scribble that if we want. We can see that this is equal to 1 plus 1 over R, 1 over R2. Just on the side here. All that matters in this V out over V in equation is the ratio of R1 and R2. So I could have chosen 1 ohm and 2 ohms. Let's say I did that. Well, now I have a total resistance of 3 ohms, which is not a lot. 3 ohms, so 9 volts divided by 3 ohms is 3 amps. Now power is I times V, is a 27 watt heater that I've made out of my resistances here. That's going to light a fire very quickly. So I'm going to burn the place down if I plug in a 1 ohm and a 2 ohm. We're going to waste a ton of power just even when this thing's not plugged in. So let's just make it let's make it a giga ohm or something like that, or a mega ohm. Right? That'll solve all our problems, right? Unfortunately, no. We'll run into another problem. Let's not be so dramatic. Let's say that I chose our original value is a 1 kilo ohm and a 2 kilo ohm resistor here, and I get my 6 volts out here. But what I'm going to do is I'm going to plug it into a 1 kilo ohm, or let's say a 2 kilo ohm load. Doesn't really matter what it is. I don't know. Let's make it 1 kilo ohm. Let's make my math slightly more cumbersome. A 1 kilo ohm load here, and I'm going to measure my 6 volts, right? I won't. In fact, when I plug this in, I'll measure it. 6 volts, great. I'll plug it in, and it won't turn on because all of a sudden I'll have much less than 6 volts here. Why? We can actually see why by looking at this. Once we've plugged something in, we've now put the thing we plugged in parallel with R2 here in our voltage divider equation. We've modified R2. In fact, what we've done here is made a new resistor. We've made an R2 prime, which is a parallel combination of 2K and 1K, which is equal to 2 times 1 over 2 plus 1K, 2/3, 670-ish ohms. All right, 2/3 of a kilo ohm. So now when I've actually have a much lower resistance here all of a sudden. This thing just thinks it's a normal voltage divider, but now I have V out is equal to 670, I'll just write 2/3 of a kilo ohm divided by 1 kilo ohm plus 2/3 of a kilo ohm. And that is, times V in, and that is 2/3 over 3/3 plus 2/3, 5/3 K times 9 volts. Great, that is going to be 2/5 of 9 volts. So 18 over 5, whatever that is, 3.6 volts. Okay, so when I plugged in my 1 kilo ohm here, all of a sudden the voltage of the thing dropped to 3.6 volts instead of 6 volts. What went wrong? What went wrong here? What went wrong is that I've now sourced a ton of current. I've actually made much more current flow through this system than would have normally. I have a much lower effective resistance here, and what that means is that my voltage drop is going to be different. But if I did a different example, if I plugged in a different device that say had a mega ohm or a giga ohm, let's just say a mega ohm, I now have a parallel combination of a mega ohm and 2 kilo ohms. In parallel, that's basically no different than just having infinite ohms in parallel here, and I'm still going to get my 6 volts. I'll probably get 5.999 volts across there. So as long as my load, the thing that I plug in, has a much greater resistance than the voltage divider, I'm okay. So that means I have a bit of a compromise. I want to make the resistances rather big enough that I'm not dumping a ton of power just all the time, but small enough that it's going to be reasonably smaller than all the things that I plug into it to avoid this error. This error, by the way, is called loading error. That's an example of loading the source or loading error. Whenever I plug in something that all of a sudden draws a lot of current, it's going to drop the voltage unexpectedly of my device. Okay, so that's what I wanted to talk about with voltage dividers. There's one last thing we'll talk about here, and that is how to make a variable voltage source with voltage dividers. Okay, so in the lab you have potentiometers, and a potentiometer basically has 3 terminals, and I'll call them A, B, and C. And the way it works basically is we're sliding an internal mechanism such that we're sharing the resistance between A and B, between A and C and B. So what this means is effectively I have a fixed resistance here. R between A and B is equal to R, right? And I have 2 resistances between A and C and B, and basically at a slide I share this R total, this RAB, between these 2 resistances. As I slide it all the way to the left, or if I crank it one way, I'll have 0 ohms and R ohms. Halfway in between it'll be R over 2 and R over 2, and then eventually it'll go to the full R resistance, R ohms here, and 0 ohms between C and B. Okay, long story short, R AC plus RCB is equal to R. Let's just call this total. Okay, but notice there's 2 resistors here. So what I can do here is I can actually connect this to a battery. I will connect this part to ground. I will connect this just to some node here, and I'll connect this to 5 volts. Okay, so let's say I do that. Let's see what I've got in here. So on my circuit board I've connected A just to ground, B to the total voltage, and I'm just letting this hang out, and it's going to be any effectively resistance between 0 and R total. I actually made a voltage divider, 5 volts, as my input, here I have RCB, which is going to be R total minus R AC. That goes to C here, and I have my other resistor, RAC, just down here. And in my potentiometer, RAC, as I twist the knob, is going to go between 0 and R total. So it's going to linearly change from 0 to R total. And let's see what I get with my voltage divider equation. Well, R2 is RAC, so I'm going to get RAC divided by R1, which is R total minus RAC, plus R2, which is RAC. These cancel out. And I just, times Vin, and I get RAC over R times Vin. And remember, as I twist this knob here, RAC starts at 0, in which case I have 0 volts, and goes all the way to R total, in which case I have V in volts. And by wiring it up this way, as I twist this, I can get any voltage between 0 and V total in a continuous way. So this is going to have the same loading error as we had in previous circuits, but it will get a continuous voltage when not plugged into anything between 0 and 5 volts. And if I want to make this a great voltage source, we just have to wait a couple weeks, and we'll hook it into what's called a follower op amp. And then we'll just get a beautiful 0 to 5 volt continuous supply without any loading error. All right, but that's getting a bit ahead of the game. For this lecture, I just want you to pick up the basic topology of the voltage divider. So we'll summarize. Voltage divider, V out over V in. It looks like this. We have V in. We have resistor R1, R2. We create a new voltage, V out. And the formula is given by R2 over R1 plus R2. That is the voltage divider formula.